All right, you guys, today we're just doing a little review for quiz 5. So first up, I'm telling you that our lines are parallel, so we know that these are parallel pathways. I usually emphasize those with a color, so I'll make them nice and red. So those are my parallels. And then here would be my transversal. So first thing that I have to do is recognize, well, what's the relationship between these two angles? And those are actually not any of my special named pairs. These are not corresponding or alternate interior or alternate exterior or same side interior or same side exterior angles. So what I need to do is really picture, well, what would happen if I took, say, this angle right here, and I slid it into its corresponding spot right here. Now I see the relationship. They're supplementary because if I slide it into its corresponding spot, now they would form a linear pair. So the relationship is that they are supplementary. Their measures have to add to 180. So I'm going to build my equation. X squared minus 12x plus 2 plus negative 10 times x minus 1, all equal to 180. And from this point on, it's really an algebra problem. I have to distribute that negative 10. So x squared minus 12x plus 2 minus 10x plus 10, all equal to 180. Okay, combine the like terms. So here I'm going to leave the quadratic. There's only one quadratic term. And then minus 22x. I'm just combining the two linear terms. And my constants, they add to 12. All equal to 180. So now I see it's a quadratic equation, right? We've been practicing a whole lot of factoring in this class. So I need to subtract the 180 from each side so that my equation is equal to 0. I cannot factor unless my equation is set equal to 0. So I need to subtract 180 from both sides. So x squared minus 22x minus 168 is all equal to 0. So now what I'm picturing, I usually picture this in my head, but I know some people like to visualize it. So I'm picturing my product and my sum. What multiplies to negative 168 that adds to negative 22? So I probably run through my options. I usually try to keep in order as I do so. So 1 times 168, 2 times 84, and then eventually I'll see, oh, it's 28 and 6, and it has to be the 28 that is the negative. So this factors into x minus 28 times x plus 6, all equal to 0. And then when I set each factor equal to 0 and I solve, I get that x could be 28, x could be negative 6. So it's a matter of which one is going to work. So if I plug back in, let's say that I try that 28. Let's say that I try it right here. So I'm looking at what would be 28 squared. Just slide over so you can see everything. So 28 squared. And then minus 12 times 28. And then plus 2. Well, that gets me something way too big, right? I cannot have an angle measure that is 450 degrees, right? This can't be 450 degrees. It has to be something that is more than 0 and less than 180. So that 28 is an extraneous solution. We were able to solve for it, but plugging it back in, it doesn't actually work. So the only one that's going to work is the negative 6. So when I plug that back in right here for x, negative 6 minus 1 is negative 7 times negative 10 is positive 70. So this right here would be positive 70. Let me just double check that this is then the supplement, 110. So negative 6 squared, right, would be 36. And then here we have plus 72, because negative 12 times negative 6 is 72. Add the 2, and we are at 110. All right, so I've just confirmed that that is the solution that works. And then I'm asking for the measure of 1. Well, these are vertical angles, so the measure of 1 has to be 70. All right, next question. We're jumping on the coordinate plane, so I usually zoom in a little tighter here. Makes it easier to see. Okay, so find the shortest distance from a point to a line. Okay, so remember that your shortest distance is that perpendicular pathway. So let me plot the point. So negative 5, 6. And then graph the line. So it's slope-intercept form, so I know that my y-intercept is at 0, negative 8. And then if I build off of that, I'm going up 4 and right 1, up 4, right 1, and so forth. I usually give myself a lot of points along that pathway. All right, so my original slope right here for this line is at 4. So my perpendicular slope has to be the opposite reciprocal. So I'm looking at negative 1/4. So from my point, I'm going to go down 1 and right 4, down 1 and right 4, down 1, right 4. So here would be the perpendicular line that slices through the point and the line. But what I'm really interested in is this portion right here from the point to the line. So how am I getting that measure? Well, I'm picturing that right triangle. I could also use the distance formula. That's fine. I usually visualize this right triangle where I have a leg that's 2 and another leg that is 8. Remember, it was 2 slopes, right? So it makes sense, since my slope was negative 1/4, here we went down 2, right 8, 2 slopes. Okay, so now I take the square root of 2 squared plus 8 squared, 4 plus 64, 68. So square root of 68 is 4 times 17, and here's my pair of 2's. So my distance, my length, is 2 root 17. Okay, next up, here I have 2 triangles that are graphed. They're plotted on the same coordinate plane. And we are to describe how to move one to the other using a series of 2 transformations. So I'm going to remind you that our answers can vary here, and there are many, many different ways you could get there. Let me make sure that W looks right. All right, so our answers can vary. How are we moving this triangle into this triangle's position? So many options. So let's say that I start one option with a 180-degree rotation. I don't need to specify clockwise or counterclockwise because it will be the same regardless. So if I'm doing my rotation, let's say that I start with L. Okay, L is at 6, negative 5. So with my 180 rotation, I just switch those to the opposite sign. So 6, negative 5 will become negative 6, positive 5. Let me just make sure I'm reading that right. Yes, negative 6, positive 5. So right here, right there will be my new L position. Let's say that I look at where A is. A is at 4, negative 3. So we're looking at, instead of 4, negative 3, negative 4, 3. So right here. Okay, and then for P, we're at 4, -7. So -4, 7. Right here. Okay, so the 180 rotation put me right here where I'm graphing it in green. And then I have to slide it into its final position. So if I slide it into its final position, if I follow my L's, I'm going left 2 and up 1. So a translation. 2 left, 1 up. And I usually do a little sketch of what it looks like on the graph. So here would be my L double prime. But since I rotate A rotates into this position right here. That means that right here would be my, my A prime. So right there is my A prime, my A prime. So then this would be a double prime right there. Okay, P would have rotated into this position, so that would have been my P prime. So this would be my P double prime right there. All right, so that's what my final draft would look like, just like so. One more option. Let's say that in scenario 2, we reflect first. So if I'm reflecting, depends which axis we want to go over. So here's my x-axis, here's my y-axis. Let's say that we start by reflecting over the y-axis. All right, so then here we're 4 away. So 4 away. Here would be my new A prime. L is 6 away. So right here would be the L. And then P, 4 away. Here would be the new P. All right, so here would be all the single prime points right in this position. Okay, so then I have to slide it via translation into its final spot right here. So if this is my L, I would be going over 1, 2, and then up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I'd be going 2 left and 11 up. So let me just write that. So a translation next. 2 left, 11 up. Okay, then what would that look like? I know that this is the L double prime. So right here would be the P single prime. So when it slides to here, this would be the P double prime right there. And then here would be the A double prime just like that. So again, the reason that I'm not labeling those 2 coordinates is because it really depends on what you choose. Do you choose to do a reflection? Do you choose to do a rotation? How are you moving it from this spot into this spot? You got some options, so I'm being flexible by not labeling the A double prime, P double prime, or vice versa. All right, next up. So here we're looking at a triangle. I'm giving you the vertices. I've already graphed it, and I'm saying let's first find the perimeter. So to find my perimeter, what really helps me is if I start by looking at all those right triangles. So I'm going to start by just boxing it in, like so. So I'm just framing a rectangle around my triangle. Okay, and then I'm just going to mark what each of these parts end up being all the way around. So here, this is a span of 8 units. Here's a span of 6 units. This is a span of 9 units. Here's 13 units. Here's 15 units. And here's 5 units. Okay, so that helps me out if I'm trying to find the measure of BO, right? It's the hypotenuse of this right triangle. OX is the hypotenuse of this right triangle. And BX is the hypotenuse of this right triangle here. So if I go OB first, I want its measure. So big square root, I'm just looking right here. of 6 squared plus 8 squared. So I have 36 plus 64, which is the square root of 100, which we love. That's a perfect square. So we end up just getting 10 for the length of OB. So this has a measure right here of 10. Okay, if I want OX next, so my big square root, okay, I'm looking at 9 squared plus 13 squared. So I have 81 plus 169, which is 250. So the square root of 250, right, I can see that it's 25 times 10. Here's my pair of 5s. That 10 stays behind, so it's 5 root 10. So that's the measure of OX right here. Okay, next I want a BX. So square root, 5 squared plus 15 squared. So 25 plus 225. So 250, square root of 250, I already solved for that. So I get 5 root 10 again. So my sides are 10, 5 root 10, 5 root 10. So I see that this triangle is actually an isosceles triangle because these two sides are exactly the same. All right, so my perimeter, if I add those up, 10 plus 5 root 10 twice, we can only combine the like terms, and the like terms mean that we have the same radicand, so the same number underneath the radical. So I can combine right here and say that my perimeter is 10 plus 10 root 10 units. All right. Next, I'm asking for area, and as we've talked about before, we actually have some options for area. Let me zoom out just a smidge. Okay, so here I'm saying specifically, let's treat it as the base is BX. So if this is our base right here, we need to figure out what is our height. So I need to go, what is the slope of BX? So I know that I'm going down 5 and right 15, which makes negative 1/3 overall. So I need my perpendicular slope. We know that to get our altitude, we're looking at this segment, this point, and that shortest distance between them is the perpendicular one, and that's our altitude. So I need the perpendicular slope. Opposite reciprocal, it's going to be a positive 3. So from this point right here to this segment, I need to go a slope of 3. So up 3, right 1. We go in the opposite direction. So down 3, left 1. And I see that that point of intersection is right here. All right, so there's that perpendicular line, but again, I'm looking for that altitude. I'm going to shade it in blue so you can see it even more clearly. Right, that's what I need. I need that measure because I'm saying that this is my base right here. Okay, so if I find BX, that's my base. I've actually already solved for that in that previous step. So find the measure of BX, that is our base. So if I go over here, right, we already solved for that. That was 5 root 10. So then I need to find the height. So the height is the measure of the altitude. So it's what I have right over here in blue. So I could use the distance formula. I can picture this right triangle, which is usually what I do. So I'm looking at this right triangle. where I'm looking at what the two legs are, and I'm solving for the hypotenuse of it. So I'm visualizing this right triangle. So this is 3, this is 9. So big square root, 3 squared plus 9 squared, 9 plus 81, square root of 90. Okay, so square root of 90, that's 9 times 10. So here's a pair of 3's. That 10 stays behind, so 3 root 10. So I know my base and my height, 5 root 10, 3 root 10. So if I visualize it, here's that triangle. Here is that base that is 5 root 10. Here is that height, which was 3 root 10. So all I'm doing is 1/2 base times height. So half of 5 root 10 times 3 root 10. That's really saying half of 5 times 3 times 10. I can multiply whatever order I want, so I'd probably take half of the even number first, so that gets me 5, and then times 5 times 3, and I would get 75 units squared. Okay, I want to remind you that there's another way I could approach it. So I could also take the big rectangle, find its area, and subtract these 3 right triangles. That would get me there another way, and it should confirm that we get 75 square units. All right, the equation of bx next. So I want this equation. So we know that that's y equals mx plus b, slope-intercept form. We already know the slope because we were down 5, right 15. So I have negative 1/3 and then x, and it's crossing right here at negative 5. Okay, midpoint of BO. So my midpoint, the middle point, average of x, average of y. So I add the x's, divide by 2. I add the y's and divide by 2. So if I'm looking at BO right here, right, I can visualize where I think it is. I can make a prediction that it's right here at negative 6, 2. That's what it looks like, that middle point. I just want to confirm it. So if I go back to my points right here, I'm taking the negative 9 and the negative 3, adding those together, and then dividing by 2. And then for the y's, I'm taking the negative 2 and the positive 6, adding those and dividing by 2. So negative 12 over 2 is negative 6. 4 over 2 is 2. So I'm confirming that I did make the correct prediction over here, right, that this is the midpoint of this segment right here. All right. We are good on the first page, so I'm going to have us flip over to the back. So on the back, I'm just having us do a bunch of proofs. I just wanted to make sure that we felt really confident with this style of proof. Okay. And I like being a little bit zoomed in just so you can see all the detail. Okay, here we go. So first off, I'm giving you a few pieces of information, right? I'm starting with angle 1 and 3 are congruent, 2 and 4 are congruent, right here. And we're trying to build to these pathways running parallel. So our goal is to connect here and here. So I know that I'm using one of the converses because I need to establish an angle relationship that will build me to my pathways running parallel. So I know that this has to be the transversal that's going to get me there. Okay, so let's start with the givens, right? We know that angle 1 is congruent to 3. Angle 2 is congruent to 4. Given. All right, so let me mark my picture. So 1 and 3, 2 and 4. So I'm giving 1 and 3 a single tick mark, 2 and 4 a double right now. So then I need to look at my picture and think, well, can I tie another pair of angles together? And I see right here, absolutely, 1 and 4 connect because they are vertical angles. So angle 1 is congruent to 4. Vertical angles theorem. Okay, so we've connected 1 to 3, 2 to 4, 1 to 4. Okay, so if we picture the little chain that we're building, right, then we need to see, well, what else can we connect, right? So if I'm connecting 1 to 4, now I can give 1 a double tick mark because those are connected, but I already knew 1 and 3 were connected, so it's going to let me circle back and finish up that 4th connection. So I can say that 2 then must be connected to 3. And I could argue that that's really substitution because I'm plugging in things I know that they are the same as, or I can picture it as a chain of 3 or more things, which I would call transitive. I would take both of those. So I'm going to write substitution first because that's what I saw first. But transitive would be fine also. All right, so if I can connect here 2 and 3 and say that those angles, they're congruent, what kind of angles are those? They're alternate interior angles. So if I have alternate interior angles that are congruent, then it's going to lock these lines into a parallel position. So ultimately then these pathways are running parallel, so segment BR will run parallel to WN. So my reason would be the converse of the alternate interior angles theorem. All right, let's tackle another one. So looking over here at B. So we're starting with 1 pair of parallels and 1 pair of angles that are congruent, and we want to end up with another pair of parallel pathways. So let me mark what my starting point is. Let's start with, I'll make them green parallels. So I'm starting with S and P that are parallel. Right, this is where I'm starting, and I want to end with I and N run parallel. Okay, so let me first just document my 2 givens. So line S is running parallel with P. Angle 1 is congruent to 2. Okay, so where can I build off those green parallels? So if those are parallel, then I need to look for a transversal that would help me connect a pair of angles, and I see it right here. So if that purple pathway is my transversal, and I know that here is angle 2, I know that 2 must connect to 3 because they're corresponding angles. So here in step 2, oh, I forgot to write the given. Let me just fill that in first. So in step 2, I'm going to say, okay, well, I can connect 3 and 2 because they're corresponding angles, because I knew that S and P were parallel. So corresponding angles postulate. So now I know right here that that takes a single tick mark. So if I've connected 1 to 2 and 2 to 3, well, I can now connect 1 and 3. That's just the transitive property. Or I could argue substitution. Do I picture it as a chain of 3 or more things? In this case, exactly 3. Or do I picture plugging in one thing for its equivalent thing? Either way. So substitution would be fine also. Okay, so remember that our end game is to get I and N to run parallel. So we're trying to get to here. Let me make this also purple. So if I look at right here, so let me focus right there on where 1 and 3 are, what kind of angles would they be? I'm just blocking out my noise. So angles 1 and 3, those are alternate exterior angles. They are congruent, so that is what is going to lock my lines, my purple lines right here, into a parallel position. So I can reach my conclusion that I runs parallel to N, converse of the alternate exterior angles theorem. All right, a couple more. Here in 7. All right, so here we have a starting point that's parallels, and we want to end with parallels. So I'm going to use that same strategy that I used in that previous one. So my starting point is that here, BC and AF, those are parallel. And we know that 1 and 3 are congruent. So let me start off by stating what's given. So BC parallel with AF. Angle 1 is congruent to angle 3. Given. How do I build off of those parallels? So let's say that I make this purple pathway my transversal. So if I block this out for a moment, I can see that, okay, if these are green parallels, then I can link up 3 and 2 because those are alternate interior angles. So angle 2 connects to 3. Alternate interior angles theorem, right? We know the parallels. That leads us to any alternate interior angles that have to be congruent. Okay, so now in step 3, since I've connected 1 to 3 and 2 to 3, I'm finishing up that three-way connection. I'm saying, well, angle 1 must be congruent to angle 2. Transitive or substitution. We've seen it quite a bit today. All of these proofs are meant to be pretty similar in how you're connecting the dots. Okay, so now, right, remember the end game. The end game is we're trying to get these purple pathways to run parallel. So if I block this part out for a moment, because I'm building off of 1 and 2, well, what kind of angles are 1 and 2? Well, 1 and 2 are corresponding angles, and since I have a pair of corresponding angles that are congruent, that leads me to my parallel pathways. So I can get to my conclusion, AB parallel to FC, because of the converse of the corresponding angles postulate. All right, one more. All right, here we go. So here again, we are given some parallels and an angle relationship, and we're trying to build to the other set of parallels. Okay, so here my starting point is that RO runs parallel with GS. So let me make those parallels blue. And then I can see that my transversal would have to be purple. I'll make it purple right here. Okay, or I can make it this one, green. They're both transversals. We just have to think which one's going to lead me to something else. Is it the purple or the green? Well, there's times that that purple would work, but I don't have any angles marked here. So that purple's not going to help us here. We're going to want to use the green because that will help us connect those angles in just a moment. All right, so now let me just back up and fill out my given. So RO runs parallel to GS. Angle 4 is congruent to angle 5. Given. So 4 to 5. Okay, so that's our starting point. That's what we're given. And we had two potential transversals here, but the only one that made sense is the green one, because down here there's no angles marked, so I really can't be using anything down there. So I want to focus on the green as my transversal. So in my next stage, if I'm looking to connect another pair of angles, it's got to be 5 and 6. So 6 has to be congruent to 5. Okay, what's my reason? So again, I'm looking at the blue parallels. The green transversal, that will connect 5 and 6 because they're alternate interior angles. I'm going to give it a single tick mark right there. So alternate interior angles theorem. All right, we've seen this connection before, right? 4 connects to 5, 6 connects to 5, so 4 has to connect to 6 also. Three-way chain or substitution, so transitive or substitution. Okay, so now if my end game is to get to FR and OG, let me just shade those in green, and then block out my noise. So maybe I'll cover this part up and then block this part out of view for just a moment. Right, how are 4 and 6 related? Well, 4 and 6 are alternate interior angles, and since I know that those angles are congruent, that's what's going to lock those pathways into a parallel position. So I can reach my conclusion here in step 4. I can say that FR runs parallel to OG using the converse of the alternate interior angles theorem. So we've seen a proof where we use the forwards and the backwards, right? Because here we built off the parallels to get to an angle relationship, and here we built off the angle relationship to get us to the parallels. So we saw one of the originals and its converse in the same proof, right? It's entirely possible that that happens. All right, I am all done. Have a good rest of your day.